Alright, so we have this problem where we're considering a function f, and we want to prove that finding the maximum on one set is the same as finding the maximum of one of these compositions on this other set. So, just to give these things names, let A be the set of all points in R3 such that the norm of x is 1. And B is the set of all x in R2 such that the norm of x is less than or equal to 1. Okay, so what we're going to prove, so we want to prove that the maximum of f on A is either the maximum of f of g on B or the maximum of f of h on B. The way that we're going to prove this is that we're going to prove that A is precisely g of B union h of B. And if that's true, then the statement that we're trying to prove follows clearly. Alright, so we want to prove that A is g of B union of h of B. So to prove equality of these two sets, we're going to do by inclusion. So if x, we'll call this x1, x2, x3 in A, then so if we take the norm of x1 comma x2, then this is the square root of x1 squared plus x2 squared. And if you add something to that, it's going to get smaller. So, no, if you add something to that, it's going to get bigger. So it's less than or equal to this thing. This is just the norm of the vector x. So if x is an A, no, what am I doing? Yes. And then, because x is an A, the norm of x is 1. So all that we're saying here is that the norm of the vector x1 comma x2 is less than or equal to 1, meaning that x1 comma x2 is a point in B. So x1, x2 is in B. Also, okay, so we have the norm of x equals 1. So if we square both sides of that, we get 1 equals x1 squared plus x2 squared plus x3 squared. And we solve for x3 squared. x3 squared equals 1 minus x1 squared minus x2 squared. And so let's see here. How do I want to write this? X3 is equal to minus 1 to the I of 1 minus x1 squared minus x2 squared square root. Where either I is 0 or I is 1. Basically, so x3, because x3 squared is equal to this thing, x3 itself is going to be the square root of the thing that we have on the right hand side, but there's two possibilities. It could be negative or it could be positive, and we don't know which one it is, so it's going to have some sign. And what I was thinking of writing here before, by the way, was x3 equals plus or minus the square root of blah blah blah, but that doesn't apply here because usually that means that x3 could be one of those two, either the positive or the negative. And here, we're not saying that it could be either one. We're saying that it is precisely one of those two. and whichever one it is just depends on whatever the value of x3 happens to be. All right, so if I equals 0, then x is in G of B. Because x1 comma x2 is in B, and then G of x1 comma x2 is going to be x1, x2, and then the square root of 1 minus x1 squared minus x2 squared, which is precisely x3. So G of B is precisely x. No, G of x1 comma x2 is precisely x. And so x is in the set G of B. So that's the case if I equals 0. And if I happens to be 1, then x is in G of A. No, H of B. And it's for the same reason. Because in this case, x1 comma x2 is in B, and H of x1 comma x2 is x1 comma x2 comma negative the square root of 1 minus x1 squared minus x2 squared, which in the case of I equals 1 is precisely x3. And so H of x1 comma x2 is x. And so x is in the set H of B. So either I is going to be 1 or 0, and in either case x is either going to be in G of B or H of B, and thus x is in the union of G of B and H of B. And since this holds for any x in A must be contained in G of B union H of B. All right. So conversely, and the converse is essentially the same exact argument. I'm sure there's a way to phrase this argument where you replace all of these, like if this and this. If you can replace all of those with if and only if statements. But sometimes it can be a little tricky to do that, and I don't think I'd be able to write a clear argument, or I would not easily be able to write a clear argument involving if and only if statements in place of if statements. So instead, I'm just going to go backwards. But we're essentially going to do the same thing that we just did, but in reverse. So let's say x is in G of B union H of B. This implies x equals x1 comma x2 comma x3, where, and now we're going to have the norm of x1 comma x2 So let's see here. If x is in G of B union H of B, then there is some point x1 comma x2 in B such that x is equal to G, x is either equal to G of x1 comma x2 or H of x1 comma x2. In either case, the norm of x1 comma x2 has to be less than or equal to 1, and this third coordinate x3 has to be of this form, where I is either 0 or 1. All right? All right. So, if we take the norm of x, this is just the square root of x1 squared plus x2 squared plus x3 squared, which is the negative 1 to the I. When you square it, is going to be 1, regardless of whether I is 0 or 1. And then you take, then you square this other term, and we get 1 minus x1 squared minus x2 squared. I don't know why I wrote a 3 there. But anyway, so the norm of x is the square root of this entire thing. And then you get a bunch of things that cancel. So this is true, and so this means precisely that x is an A. So thus, G of B union H of B is contained in A, and hence A is equal to G of B union H of B. And then the conclusion that we want to prove follows immediately, because we want to prove that the maximum of f on A is either the maximum of f on G of B or the maximum of f on H of B. And that's obviously true because you're saying that because the sets A and G of B union H of B are the same. So taking the maximum over one set is the same as taking the maximum over the other set. And there is some comment here. I don't know if it was part of the exercise statement or if it came earlier in the section. But there was some comment on how this is going to be useful later on. Because we see here, the maximum of we're taking the maximum of f on a subset of R3, and then we're comparing that to the maximum of two functions evaluated over a subset of R2. And so you're reducing the dimension of your search space. And so that, I think that's the key thing here, because we can see that this exercise there, it isn't too tricky. There's not a lot you have to do. So the point of this exercise is not to be difficult. The point of this exercise is that this is a useful observation that we will use presumably when finding maximums of functions defined on Rn, and it will help us sort of reduce the dimensionality of the space that we're searching over. But in any case, we've done everything that we need to do for this exercise, and so that's it.